In our usual rectangular plotting system, we locate positions by measuring horizontally and vertically. In the polar coordinate system, we locate points by using radius and angle measurements. We list them as the coordinates of the point r, theta. Graphing equations given in polar coordinates using r and theta is usually not easy to do by hand, so we often rely on machines to do the hard work for us. I don't think any of us would do a good job at graphing an example like this with pen and paper. But it is useful to be able to see conceptually how a polar graph is formed and why it is shaped the way that it is. One technique to help with this is to graph the equation in the rectangular coordinate system first. I don't mean convert an equation in r and theta into an equivalent one with x and y. We do sometimes do that in other contexts. Instead, take the given equation in r and theta and plot it with theta on the horizontal axis and r on the vertical, just as we might with x and y. This allows us to see the behavior of the output values in the system we are used to. Then try to imagine these same values being plotted along a radius as it rotates around the origin. To illustrate the idea, here are some sample input and output pairs, r and theta, plotted in both coordinate systems. You have to kind of adjust your thinking. Instead of points rising higher when output values increase, they get farther away from the origin, in whatever direction that might be. Next, we'll investigate several polar equations using graphing software. As described earlier, I've set up two axes systems side by side. On the left is rectangular coordinates, and on the right is polar. And there's no axes labeled with values, but on the left here, these gray vertical lines are pi over 2 pi, 3 pi over 2, and then the black bar is 2 pi. So that's corresponding to inputs for theta for one revolution of the circle. And the black bar you see there is representing basically the angle being drawn. So what happens is we'll graph an equation in both systems, and then as we pull through the values, on the left you see the heights vertically, and on the right the output measurements are going along the radius as we go around. And the idea is to try and make the visual connections of how the behavior of the outputs creates the polar graph. So for instance, let's do a very simple one. This is just a constant function. This is r equals 2. So for all values of theta, the radius is 2. And if you watch as I pull through here and it draws the polar graph, what I want you to try and keep an eye on is the red bar. That's the actual output value. That's the radius value. The black just represents what angle is being entered at the moment. But so the red bar on the left, you see it always stays the same height, so we get a flat line, similar to y equal 2 or something. But on the right, as we pull it around, it does trace a perfect circle because the radius is always staying the same amount. Okay, that's not too interesting. I'm just trying to get you used to how the graphing setup works here. So let's put in just a diagonal line on the rectangular system. So this is just like a y equal x type of equation. But remember, we're doing r and theta. And so this says that as theta increases, the radius values steadily increase also. So try and picture this as the radial arm goes around the radius. The larger theta gets, the larger the radius gets in a nice, even step by step. So we'll start dragging it around, and you, on the right, watch the red bar. It should match the length of the one on the left. And as we increase our angles, the radius increases also. And we draw a nice spiral. Okay, before we get to more interesting graphs, I wanted to show you what happens when we do get negative radius values. So I'm going to go ahead and just put a negative on that equation so we're getting the same straight line. segment on the left, but it's going into negative values down below. And so what you'll see on the polar graph is, now remember, the black bar is what the angle actually being used. Right now we're in quadrant 1, but it's graphing in quadrant 3 because the R values are negative. And so this is going to draw a spiral, but the entire spiral is being drawn with negative radius values. So this is one of the cautions when you look at a polar graph. Even if you have a machine do it for you, you can't always assume that what you see was drawn with the angles that it appears to match up to, because sometimes they come from negative radius values. Okay, let's do an interesting one. This is the equation R equals sine theta. So on the left you see a normal sine wave graphed in the usual system, 1 period. And it might be hard to guess what this actually graphs as if you haven't seen it before. So let's just watch the behavior. In quadrant 1, it rises steadily to a height of 1. Quadrant 2, it goes back down to 0. And it looks like it traces a perfect circle in the polar graph. In fact, it does. Now we go into negative R values, and you see we get the same circle redrawn. So sometimes it only takes 0 to pi to draw the whole shape, and then it just repeats itself. Let's make that a little larger. So I'm going to put 2 sine x on here, so that stretches the amplitude on the left graph. On the right, that has the effect of expanding everything from the center out, so we get a larger circle. And I'm going to show you what happens as we change the vertical placement on the left of that graph. So we're going to add, we're going to add a vertical shift. So if I shift the graph on the left up, all I'm doing is I'm adding to the output values. That's going to shift the radius values out. But you'll see something interesting happening. We get a large loop within a small loop. So let's see how that came about. Okay, so look on the graph on the left. We start off quadrants 1 and 2. We rise and then fall. So that should create sort of a big loop in quadrants 1 and 2. Quadrant 3, we're starting off positive, but then it's going to change to negative. And so when that reaches 0 value on the radius, that's when it closes up to the origin there. And then it shifts to the opposite quadrant. And then it does a symmetrical follow-up, and we get a small loop within a big loop. So just a little foreshadowing, what happens in calculus sometimes is you have a computer draw the graph and everything, but then in calculus you'll need to figure out, for example, that small loop, what exact angle values created that, what radian values. And if you just look at the finished product, you can't tell. Is it 0 to pi? Because it's sitting in quadrants 1 and 2. But no, that's not correct at all. And so it helps to see the rectangular coordinate graph, because then you can see here, like, oh, it's when it went negative, this territory right here. And then you can try and figure out what theta values those were to make that happen. If we shift it down below the axis, you get similar behavior happening, just the loop within a loop in a different part of the, happening for different values. Okay, so this brings us to a very famous one. This is, we're going to put in sine of 2x, which creates, you'll see the graph's a nice four-leaf clover looking shape. This is a famous example used in trig classes because it illustrates the graph going into positive and negative territories. But so this is the standard one. You'll notice that on the, before we draw it, each quadrant seems to have its own little set of the sine waves. So we got an up, down, up, down. So in quadrant 1, the radius value goes up and then back down. So it should draw a nice little loop. Okay, now in quadrant 2, it goes opposite, negative radius values. So our black bar is the angle actually being used. That's in quadrant 2. The red bar is what the output is. It's negative. It's graphing in quadrant 4. Quadrant 3, we're back positive again, so graphing in the quadrant we would expect. And in quadrant 4, it's backing up and graphing in quadrant 2. Okay. Let's see that done nice and smooth, so hopefully you can follow along visually and see how that gets drawn. All right, everyone believes it, right? Okay, we're going to, I'll show you what happens if we move this out. So if we shift that sine wave upwards so that it's all positive and no x-intercepts, or just barely. Actually, let's make it, I'll shrink the wave down so there's no x-intercepts at all. Then what we would expect is some, pulling in and out, but nothing near the origin, so there should be no crossovers into the opposite quadrants. And we'll create a nice little peanut shape. But if we lower this back down, then we start getting those crossovers. And if we do it just right, we get our 4-leaf clover, but then it'll go back the other way. Okay. If you play with these, let's do a cosine one. This is a cosine of 3 theta. Something weird happens because if you have a 2 theta, it made 4 little loops like a 4-leaf clover, and then I put a 3, and this one only has 3 loops, not double like 6 like you might expect. So what's happening here? Let's see how this gets traced out. You see lots of ups and downs. And when we start, you'll see, so there's the positive part. It creates half a loop, looks like. Then it goes negative. So it's opposite quadrant, creates a loop. Then it comes back positive, creates a loop. Now look what happens here. It's going negative, and it completes that loop. And so this is another example where we have the entire graph drawn from 0 to pi, the first 2 quadrants. And if we keep going, it's just going to repeat itself. Okay, just for fun, let's make one a little more interesting. A little more going on, I guess. Okay, this is 1/2 plus 2 cosine 5x. Lots of ups and downs. So what would we expect? You'll notice that the positive parts are higher than the negative parts that go down. There are 1, 2, 3, 4, 5 ups and downs, it looks like. Let's see how this draws. Look, I made a nice sand dollar for you. So let's see if we can figure out why there are 2 different size loops and they happen to be nested inside of each other. So that's because the negative parts did not stretch out as far as the positive ones. So if we watch how that gets drawn, here's a positive loop. Then it goes negative. The negative ones are drawing the smaller ones in opposite quadrants. So you'll see the negative ones on the lower quadrants there. But then when it gets around, then those roles swap and it fills in the missing pieces. Okay, I've got excuse me, one last one, a pretty one to show you, but I want to show you a weird one first, just so you can hopefully get used to how this sort of works. This is just r equals secant theta. I would have no idea how this actually draws if you just try and guess. So we have the one period of the secant graph on the left, and secant is, remember, a strange graph. So this has vertical asymptotes. How is that going to work when it gets converted into the polar system? So at first, it seems to be pretty well behaved. So you look at the red bar, it just gets a little longer as the angles go. But then the angles get, or the radius values get much, much, much longer. And in fact, they're going to go infinite when we get to the end of that quadrant. So interesting, if you look at what's happening, it's actually drawing on the polar graph a straight vertical line, starting at the origin and going up. So in the polar system, it is hard for it to draw a straight line. The radius has to get increasingly longer as it goes towards the pi/2 angle in order to keep that line going. And that's exactly what happens. And when we get to the asymptote, it suddenly jumps, and now the negative asymptote is coming in. So you saw that line just suddenly fill in because it's coming in. It actually shouldn't be filled in quite yet, but it's coming in from the other side. So the line gets completed in two different parts. It goes off to infinity on the top and then comes in from the lower and finishes it. And then if we keep going, it'll draw it twice. So you can work out algebraically why this creates a straight line. You can verify that, yes, it really does create a straight line. But it's, if someone said, how do you create a straight line in polar, I would never have guessed. Oh, sure, secant, of course. Okay, just for fun, this is supposed to draw a butterfly. What are the odds? Okay, so look at the behavior. This is a semi-complicated equation. Don't worry about it for the moment, but we have loops at different heights. So, well, they should be loops. So these are going up and down, and then they go into the negative territory, and they're all sort of slightly different contours there. So let's see what happens. Okay, so we're going upward in quadrant 1, and we come back. And then similar shape in quadrant 2. Now it's going to go negative for a second, so it draws a little bit of that opposite quadrant, and then it closes that little loop. And then we have some more ups and downs. What do you think? Butterfly? Not bad? All right, I said that was the last one. I have one bonus one for you. It's sometimes interesting to see what pretty regular types of graphs we're used to translate into the polar system. So this is r equals natural log of theta. So on the rectangular version on the left, you see the exact natural log graph you're hopefully used to. What happens when we put this in the polar? So it's the negative asymptote that's interesting here. So this is going to come in quadrant 1 when we graph it as negative huge radius values. And then they slowly come up and reach 0. And then once they reach 0, it behaves kind of like a spiral. It just gradually goes up. And it makes a nice little curlicue, for lack of a better term. All right. I hope that helps conceptualize it a little bit. Enjoy your polar graphing.